help you with that part. Okay. Okay. The periodic table, we talked about the periodic table. First of all, I want to make sure that you can hear me and you can see the page that I'm sharing now.
Yes, we can both see and hear you.
Okay, is the periodic table of the element. The element groups. So there are 4 different groups. One is the main group element that includes the group 1, 2, and then group 3, 4, 5, and 6, and 7, 8. The one with the green color. These are the main group elements. Based on the name we talked about, the alkali metals, you are responsible for the name for alkali metals, alkaline earth metals, noble gases, and halogens. The chalcogens and the other ones, you don't have to memorize it, but and they are not very common in different books. So these 4, you need to know the name for them. Based on the main, you have the main groups, and you have transition metals, you have lanthanides and actinides. So those are the major, groups that you need to know, because if you are getting a question with the element, you should be able to locate that element in the periodic table based on which group does it belong to, how many valence electron does it have, what is the classification, is it like a transition, lanthanide, actinide, or what is the. So for example, sulfur, so for these you have to use a periodic table. What's the name of the group that you have, like chlorine? So group chlorine is a group 7A, and then you have the name of the group is halogen. Sulfur is in group 6A, and the name of the group is chalcogens. So fluorine, same thing. What does it mean if the elements are in the same row of the periodic table? If you have 2 elements in the same row of the periodic table, what does it mean? Let's say if you have sodium and magnesium. In periodic table, you find sodium and magnesium. What does it mean that they are in the same, in terms of the electron configuration? Any response?
They have the same valence?
Say sodium has 11 electrons, magnesium has 12 electrons. So the maximum number of electrons that goes to level 2, level 1 is 2 electrons. Maximum number of electron goes to level 2 is 8 electrons. So no more electron can go to level 1 or level 2. Level 1 can take only 2 electron. Level 2 can take only 8 electron. And so we have 1 more electron left, and that would go to level 3. So we have n equal 1, n equal 2, and n equal 3. The last energy level is n equal 3. For magnesium with 12 electron, you have 2 electron going to the first energy level. You have 8 electron going to second energy level, and there's 2 electrons left, and the 2 electron goes to the last energy level. But you have n equal 1, n equal 2, n equal 3. But the sodium and magnesium are on the same energy level or in the same row. So they have the valence electron are going to the same energy level. Valence electron for sodium is going to level 3. Valence electron for magnesium goes to level 3. If you bring in potassium, potassium has 19 electrons. Sorry, I wrote potassium and I was thinking of calcium. So you have 19 electrons. With the 19 electrons, level 1 would take 2 electrons, level 2 would take 8 electrons, level 3 would take 8 electrons, and that's level 4 would take 1 electron. So between sodium and potassium, sodium is in row 3, and the potassium is in row 4. So potassium has valence level 4. Calcium in level 4 has 4 valence, 4 energy level, and the valence electron go to n equal 4. Valence electron would go to n equal 4. That's the difference based on the electron configuration. And the lanthonide actinide, I already explained about that, why they are outside, and more of a theory. Now we have more important questions. So when you look at the periodic table, you have the based on the periodic law, when elements are arranged in a periodic table based on increasing atomic number going from left to right, the way that it was arranged by Dmitry Mendeleev, the elements, they fall into groups in the same column, that in this group, they actually had similar properties. So if they had similar properties, so the property of the elements, they were repeated periodically. That's why it's basically the periodic law. So it's kind of explaining about the periodicity of the property of the elements. So if you have the element lithium in group 1, sodium, potassium, rubidium, cesium, and francium, so all these elements, they behave similarly. They have very similar chemical property. And the reason for that is that all of them, they have 1 valence electron. Lithium has 2 electron and 1 electron. Sodium, you saw it was 2 electron, 8 electron, 1 electron. So sodium has 3 energy level, but 1 electron on the last energy level. Potassium has 4 energy level, but 1 electron on the last energy level. So they have same number of valence electron. Then since the electrons in the outermost shell is going to determine chemical property, these elements, they all behave similarly in terms of the chemical property. Same thing for group 2, you have 2 valence electron for each one of them, and they behave similarly. So when you say element belongs to alkali metal, that means that they are very reactive. They have 1 electron on the last energy level. When they lose electron to become stable, they only lose 1 electron. An element in group 2, they have similar property. They lose 2 electrons to become stable. They are found in the earth crust, because that's why they are called alkaline earth metals. And then you have group 1A, why they are called alkaline, because if you add them to water, it would make the water very basic. So you get the periodicity, and those periodicity, they have the periodic property or similar property for groups. They are very common for main group elements. For transition metals, you have them, but there are more exceptions. So for 1045 and for undergraduate, we look for more of the main group elements, like how they behave when they are in a group, even though that property, it repeats itself in transition metal and for the inner transition metals, but there are some exceptions. We just have to know that there are some exceptions. So the theory that if they are increased by the atomic number and all that, I have included here. I was going to mention it, but if there's anything that I would not mention, please go back and review it. These are coming from the PowerPoints, really, that you have them in the D2L. Okay. So they have the elements in the same row, they have same valence shell. So as I said, sodium and magnesium, they are in the same row and they have the same valence shell. So in theory, everything is covered. The examples are the ones that you need to kind of pay attention. It's going to hopefully make it more clear for you. Atomic radius, basically we're trying to look at this periodic, the trend in the periodic table. One of the properties of the of the element in periodic table that is very obvious and it shows a trend is the atomic radius. How do they measure the atomic radius? If they have like the center to center for covalently bonded molecule, like for fluorine or for chlorine or for example, bromine and iodine, they measure from center to center, and then they would divide this by 2, and that's how they measure the atomic radius. So basically, if you have 2 like atoms, they measure the length between the 2, which is called the bond length, and they divide by 2, you get the atomic radius. Now you have the atomic radius, and if you look at the halogens going top to bottom in a periodic table, the atomic radius is increasing. Okay, atomic radius is increasing. And why is atomic radius increasing if you're going top to bottom? So fluorine has 2 energy levels, chlorine has 3 energy levels, and bromine has 4 energy levels. Okay, when they measure atomic radius, basically in the lab, the measurement is based on the bond length, but definition is the distance from the nucleus to the outermost shell. So distance from the outermost shell is increasing as you go up down, because every time you're going down, you're adding another energy level. So this distance is increasing. So in a periodic table, up, down, the atomic radius is increasing, and you should be able to predict if you are given 2 elements. You look at the periodic table, if they are in the same group. If you are giving, for example, iodine and chlorine, you say iodine has higher atomic radius because it has extra energy levels. The trend, if you look at the trend, how is changing, see, up, down is increasing. From left to right is decreasing. So up, down is always easier for the radius for someone to understand, because energy level is increasing. And as the energy level is increasing, is going to, the distance from nucleus to the last energy level is increasing, and the radius is increasing. So what happens if you're going from left to right in a periodic table? Y is decreasing. Okay, so any idea?
The electrons?
If you're going from left to right, electron is increasing. So if the electron is increasing at the same time, the charge of the nucleus is increasing. Okay, the charge of the nucleus is increasing. So let's say if you have 11 electrons, and then you have for magnesium, you have 12 electrons. For the 12 electrons, you have 12 protons, and you have same energy levels. So you have 3 energy levels for sodium, and you have the same energy level, same number of energy level for magnesium. So you have you have electrons. So they are from same distance, right? Almost same distance, because it's from nucleus to energy level 3, nucleus to energy level 3. Both electrons are attracted to the nucleus based on electrostatic attraction. So you have the positive charge in the center, negative charge in the electrons that you have, positive charge, and then electrons carry negative charge. So this attraction is attraction between opposite charges. Which attraction is stronger? You have more opposite charge, greater value for opposite charges, or smaller value for opposite charges? Which attraction is the stronger? If you were being electrocuted, you want to be electrocuted by a lightning, or by something, a device that is battery operating. So the higher the magnitude of the plus charge, this attraction is going to be stronger. And since attraction is from center to the outside, so basically it's pulling the electrons in, the stronger the attraction in the nucleus, or the stronger the charge of the nucleus or power of the nucleus, this attraction is going to be stronger. And if it is stronger, what's going to happen to electrons? They are going to be shifted inside slightly, right? Does it make sense? And since they're going, electrons are going to be shifted inside, the radius is going to decrease. So from sodium to potassium, we see that the radius is decreasing, and then same thing. These are going to the general trend. Okay, the general trend is that radius or atomic radius is increasing this way. Increasing this way, or is increasing this way. Because if you go up, down is increasing. If you go from right to left is increasing. So radius is increasing this way. And there are some exceptions, okay? So if you go from each level, atomic number is, the energy level is increasing from lithium to sodium to potassium to rhodium in the periodic table in a group. And then if you are going across from left to right, the atomic radius is decreasing. Then you have a big jump because the energy level is increasing, and then it would gradually decrease. There are some exceptions here. There are some exceptions, but general trend is that increase from one level to next level, like from lithium to sodium is a big jump. Sodium to lithium to sodium to potassium is a jump, is increase, but then it would be a general decrease for the radius. Okay. The electrons that are inside, okay, electrons that are in the inner energy level. So you have 2 electrons, and then you have 8 electrons in the energy level 2, and then you can go up to like 18 electrons. But if it's the level 3, they would have only 8 electrons in the last energy level. So the nucleus is kind of covered by other energy levels. This is called shielding effect. The valence shell is going to be shielded by core electrons or the inner shells. So that kind of blocks this attraction, the electrostatic attraction from the nucleus as well. Since this electrostatic attraction is shielded or blocked, going up, down, this attraction over the last energy level is going to be decreasing, and the going up, down, the radius is going to go up. But if you are going from the left side, from metal to non-metal, when you're going from metal to non-metal, because this attraction is happening in the same energy level, there is no more shielding of the inner level. Everything is added to the same energy level. At the same time, the power of the nucleus is increasing, then the size of the atom is decreasing. Any questions about the size of the atom or the trend in the periodic table for the size of the atom? Questions? Which one would be, which one would have higher radius, fluorine or barium? So in order to answer that question, you would go to the periodic table, you find the fluorine up here. You find the fluorine at the first energy level, you find the barium on the 6th energy level. Since fluorine compared to the barium, so barium would be higher. Very good. For the ionic radius compared to its neutral atom. So sodium with 11 electron has 2 electron in energy level 1, 8 electron in energy level 2, and 1 electron in energy level 3. Now, what happens if sodium loses 1 electron? If sodium loses 1 electron, is going to change to sodium 1 plus, is going to change to ion. Now we have 10 electron, 2 electron on the first energy level, and 8 electron on the second energy level, and there is no third energy level. Which one is going to be larger? Is the sodium or sodium ion? Obviously, is going to be sodium, because sodium has 3 energy levels, sodium ion has 2 energy level. That's one factor. Loss of a shell is going to decrease the radius. Second factor, how many protons you have here is 11 protons. 11 protons for 11 electrons. So the attraction, the electrostatic attraction is going to be from 11 plus charge with the 11 minus charge. So it's kind of 1 to 1. It's just one, they use that in like kindergarten. They say the ratio teacher to student cannot be more than 5 students per teacher. Why they do that? Because they want to make sure that the attention is not divided over like too many students, so they have control over little kids or younger students. But when it comes to sodium ion, you have 11 plus charges, 11 protons, and you only have 10 electrons. This is like if you have 2 teachers per 1 student, or you have a teacher and half, or you have 6 teachers and 5 students. What's going to be like if you're borrowing extra pair of eyes to watch them. So the attraction and the attention is going to be greater, and the electrons are pulled stronger toward the nucleus, because now the charge of the nucleus is higher, and the atom is going to shrink, and the size of the atom is going to be lowered. So sodium is going to be greater in size compared to sodium ion. Same thing for aluminum versus aluminum ion, and this diagram shows that aluminum ion is much smaller than the aluminum itself. This is for cations. Okay, what happens in anions? If you look at this picture, the picture shows that anions, they gain electron, they have negative charge, and if they have negative charges, then what is making this size increase is basically the opposite to the explanation we had for the other one, for the cation. So if you have oxygen, 8 electrons, you have 2 electron and then 6 electron, and then oxide with 2 minus, after gaining 2 electron, you have 2 electron and then 8 electrons. Okay, what happening to the attraction? Here you have 8 electron and 8 protons. So 8 electron is pulling these 8 proton or 8 positive charge from the nucleus is pulling the electron inward. Okay, and it's a kind of 1-to-1 ratio. When oxygen changes to oxide, now we have 8 protons. Okay, 8 plus charge, 8 protons, but you have 10 electrons. With 10 electrons, so the attraction is going to be kind of weaker because you have less power for the nucleus. So the power or the positive charge in the nucleus is decreasing. As a result, the electrons are pulled in loosely. And if it's just like, it's like the younger children, as if you take your eyes out of them at the playground, they like to go further. They like to move around. They like to be, finding their, trying their wings and all that. So electrons are going to move slightly outward. So electrons are going to bond looser to the nucleus. And since the definition for radius is the center to the outermost shell, now the outermost shell has shifted out. Because the attraction is less from the nucleus, the other problem is that you had 8 electrons before, now you have 10 electrons. If you have 10 electrons, these electrons, they don't like each other. One electron, another electron, they don't like each other. And if they don't like each other, they repel each other. And as they repel each other, they try to get more distance from each other. And as they try to get more distance each other, they try to make the circle bigger. And if they make the circle bigger, that means that the radius is going to increase. This part of the video, you need to watch it a couple of times because I do explain both factors. But if you didn't get it now, make sure you go back and watch it again. Just to remember that there are two factors. One, the charge for the nucleus or the ratio of charge of nucleus to the electron is decreasing. So the attractive force is less significant. Second, electron repulsion on the last energy level after gaining electron is going to increase, and that electron repulsion is going to create repulsion force between the electron, and they try to make the circle bigger so they have more room. And that's what's happening going from sulfur to sulfide ion. The atomic radius for sulfide ion is greater. Question. Ionization energy, that's the next trend in the periodic table. So first you need to know the definition for ionization energy. We have first ionization energy, we have second ionization energy. First ionization energy is like sodium has 11 electrons, minus 1 electron, it changes to sodium ion. You're taking the first electron, that is the sodium ion, with the 10 electron now. A second ionization energy is minus a second electron, okay? Minus electron, and this is a second electron. If you remove second electron, your sodium is going to have now 2+ charge. And what happens to sodium after you remove 1 electron is going to be a lot more stable. Now you have 10 electron, just like neon, and very stable. So removing 1 electron, creating more stable species, it should not be like huge problem, even though you have to spend some energy to remove the electron. But if you want to remove electron from something that already has positive charge, so the nucleus is stronger now with the positive charge, then is going to make it much harder for it to remove the electron. That's one problem. The second problem is neon, sodium with 1+ charge looks like neon. Neon is very stable, and since it's very stable, removing electron is going to make it unstable. So the second ionization is going to be much higher than the first ionization for sodium. And this is not possible with like a normal amount of energy. You have to put a lot of energy to remove electron from sodium ion. So that's the definition between first ionization and the second ionization. But what we're trying to find out here in this chapter is also the trend. If you are going up, down in the periodic table, what happens to the ionization energy? Because ionization energy is defined by the amount of energy needed to remove electron from outermost shell, okay, lithium, and then you have the potassium. Lithium has 2, sodium has 3, potassium and rubidium. So potassium has 4 energy levels, and rubidium has 2, 3, 4, and 5 energy levels. For all of them, you are taking electron from outermost shell. Which one is easier to remove? Lithium or rubidium? Which one? Which electron is easier to remove? Electron from lithium or electron from rubidium? Knowing that plus charge is right here for all of them. Which one is easier to remove electron from? You can reply in chat or use your mic.
Rubidium?
Rubidium is easier to remove because it's a longer distance. Electrostatic attraction, they are stronger when they are close to one another. You could always walk under the power line and don't worry about it. You're not going to be electrocuted, but you cannot touch the power line. because you get too close to it, and you cannot get very close to it either. So the longer the distance, the weaker this attraction is going to be between the nucleus and the last energy level. So removing electron from smaller distance or closer to the nucleus is harder than if this is longer distance. And if it's the longer distance, it's easier. So what does it say? As you go up, down in the periodic table, ionization energy is decreasing. So ionization energy is going to be lowered. If you go up, down, what happened to the size? Do you remember? If you go up, down, the size is increasing. Ionization energy is decreasing. Ionization energy is decreasing because the size is increasing. So it's opposite to the size. I want to make sure that I have something about the isoelectric. Isoelectric. What does isoelectric means?
I have a question about the last. So the ionization energy +1, and so what if it is in the I guess let's say the second period, like magnesium, the ionization energy for magnesium, how would that look like?
Ionization energy for magnesium, you have the first ionization energy first, and then you have second, and you have third. Okay, first is some energy, second is higher than the first one, but the third is much higher than the second one, because when it gets to this, when it gets to the second ionization energy, now you have neon, looks like neon. Okay, and then removing electron after this, after the second, so the third ionization energy is going to be very high compared to the second one. Good question. So the third one for magnesium is going to be much higher than the second one, and this is higher than the first one. Always second one is higher than the first one because the power of the nucleus is increasing. But whenever you reach to a stable configuration, and then you're trying to remove from stable configuration, electron configuration, like especially if it's already like a noble gas, is going to make it much harder. Was that your question?
Yes, yes,
Okay.
that was my question. Thank you.
Perfect. Any other questions? And then there are some other variations here. Let's say you have like a, ionization energy is going from, for beryllium, it's going to be higher than barium. And then for nitrogen is higher than the oxygen. That has to do with the stability of the electron configuration. So for beryllium, for Be, you have 1s2, 2s2. This is a filled, okay, filled orbital. The orbitals are full. But when you go to boron, you have 1s2, 2s2, 2p1. Removing electron from filled orbital is harder than removing from unfilled orbital. The p orbital, if you have 3p orbital, if you get 3 electron in there, is called half filled. If you get 6 electron in there, that's full. For s orbital, 1 electron is unfilled, 2 electron is full. And for p orbital is different. P orbital, you have half filled. So if you have like a 3p3 is half filled, and 3p6, this is filled, okay? Filled and half filled. So if you have half filled, it's semi-stable, but filled is very stable. Removing electron from filled and half filled is harder than unfilled. So anything in between is going to be unfilled. And half filled, like for d orbital, is like if you have 5 electrons in d orbitals in each level, that's half filled. If you have 3 electrons for p orbital, that's like half filled. For sulfur, the 1s, it doesn't count as the half filled, but anyway, you have to spend some energy. But when it changes to s2, which is filled s orbital, it's going to be very hard to remove electron from filled orbital. And s2, because the energy level is not filled, is lower than if you were removing from p6. p6 is very stable. Okay, so if you have a p6, that's very stable. It's like a filled shell. Filled shell, that's most stable. Filled orbital is stable. Half filled orbital is stable, but is not as stable as the other. Okay, so ionization energy, first, second, and third, see that the number is increasing. Okay, ionization energy. And then whenever you reach to a part that it's actually you're removing an electron from a filled shell, it makes it much higher. Like this is like ionization energy 2 for potassium is 10 times, almost 10 times higher than the first one. But when you go from 2 to 3, it's not even double. Okay, so it does increase, but there's like sometimes there's like big jump, and when you see the big jump, that means you are removing electron from a filled shell or very stable situation. Like for calcium, calcium has 2+ charge, right? And when you have calcium 2+ charge, that's the time that it reaches electron configuration for a noble gas. Removing electron configuration from noble gas is very hard, and you have to spend a lot more energy for that.
I have a question there. So ionizate for the first one, potassium, ionization energy 1, that after that it is now argon, correct? So
yes,
shouldn't the ionization, oh, that's 3,000. I'm sorry.
yes,
sorry.
it's
I thought
like
that was
10
300.
times more. Yes, I saw. Yeah, if you read this as a 305, then it's smaller, but it's actually 3,000. Yes,
Sorry.
you're right. Okay, so the ionization energy, this is the first ionization energy in general, is increasing up down. Okay, ionization energy, I'm sorry, it's decreasing up down because the size is increasing up down. It's opposite to the size. You're removing from longer distance. Okay? As you go from left to right, ionization energy is increasing as well. Okay, so radius increasing. Let me put it this way. I think students found it easier if I put it diagonally. So radius is increasing this way. This is the R is increasing. Okay, R value is increasing. And then ionization energy is increasing this way. Ionization energy increasing. So the ionization energy increasing from bottom corner to the top corner, that basically covers down up and left to right, is going to increase. And about the first ionization, second ionization, we talked. Now, questions about ionization energy. It's just to know that the trend and know the exceptions when you're going to get to like more stable situation. If it's a half filled or filled orbital, and removing electrons is going to make it much harder. Next term is called electron affinity. What is electron affinity? Electron affinity is like if you are giving electron, let's say you have fluorine and you are going to add 1 electron to fluorine, that is going to be fluoride ion. there is like energy involved here. Some elements, they lose, when they gain electron, they are going to, at the same time, lose energy to environment. So it's basically exothermic. For others is endothermic. That means that is going to, when you are giving electron, ionization is removing electron, here you are giving electron. Delta H value, delta H negative means loss of electron or exothermic, and delta H value for positive means endo. Endo means that is accepting, you must give electron, you must give energy. Exo means that it's losing energy to environment. It's going to lose the, okay. If you give electron to fluorine, what's going to happen? Energy would be lost or needed? Fluorine.
It's exothermic?
Exothermic. And what does it mean is exothermic? It means that fluoride is more stable than fluorine. If it's stable, that means it has less energy. Okay, so what happens to the difference in energy? It's been given to environment, and that makes definition for exothermic. So why fluoride is more stable than fluorine? Because fluorine is 1s2, 2s2, 2p5, but fluoride is a 1s2, 2s2, 2p6. This looks like fluorine, and this one looks like neon. So it goes from less stable to more stable. That's why energy is being released to environment. And these values are different. So you could see some of them, in some cases is gain of electron, other cases is lose of electron, lose of energy. I have to repeat this. Electron affinity is based on gaining electron. In some cases is lose of energy. Other cases is gain of energy. Meaning that some cases is going to be exothermic and other cases would be endothermic. And that depends on the electron configuration of the element you're dealing with. The electron affinity for chlorine is 348, fluorine is 322, okay? And how could you justify this difference between the fluorine and chlorine? Because we were expecting for fluorine to have the highest electron affinity because it likes the electron, but if you look at the values, chlorine is higher than the fluorine. The reason for that is that fluorine is smaller. Fluorine has only 2 energy level. So fluorine is basically is like a 2 shells, let's say 2-bedroom place. And then chlorine is 3 energy level, a 3-bedroom house, 2-bedroom house, or 2-bedroom apartment, 3-bedroom apartment. Incoming guest is going to be welcome here and also would be welcome here, but here is going to be more welcome because there is also the desire and also the physical amenity or whatever the possibility is more comfort for the electron to come to larger surface than to this smaller surface because of the electron repulsion, because it's a smaller radius or a smaller circle that electron has to be added. That's why fluorine releases less energy compared to chlorine. I put that in a question and answer, but I want to make sure you see the numbers as well.